All right, let's start our last talk. Thank you everybody who survived. And our last talk is the second talk on geometric recursion by Ron Harris.
So, first of all, I would like to thank the organizers for a fantastic conference. And I think also we should thank the administrative staff who has helped us through all the event very nicely. So let's give them a hand. Okay, so let me recap a little bit. First of all, let me show you now the revised plan. We unfortunately only covered that and then a bit of this, so things have shifted. So we have to go a little faster if we want to do the whole program here. But maybe I will actually not try to fully plow through everything, and but try to keep the pace from yesterday instead, so it's easy to follow. So I just remind you that we are considering, you know, the category of compact-oriented surfaces, and then we are considering the category of vector spaces, and we are looking at a functor from surfaces to vector spaces, and that's what we are calling a pre-category, a pre-target category, sorry, a pre-target theory. We are looking for functorial assignments inside these vector spaces, so they are inside, of course, the mapping class group invariant part of these vector spaces for each surface. And then I gave you, many examples. I will skip those right now, of course, and I will just remind you that the precise category of surfaces is compact-oriented surfaces of negative Euler characteristic with a mark point on each boundary component, together with an orientation of the boundary such that it splits in minus and plus, in and out, and we want that the inclusion of the ins into the surface gives an isomorphism of pi 0. That means that there is one in for each connected component. And so, I draw two examples over here again, but I just want to quickly go past this. The vector spaces we're interested in are Hausdorff, complete, locally convex topological vector spaces.
So you require a boundary component, right?
Yes, that is part of that.
Okay.
I have just a suggestion.
Yeah.
To use group points instead of categories, because of the rule it's its own isomorphisms here.
Yeah.
It's because of categories in
Okay, I agree.
flavor.
Yeah, I agree. Okay. Right, and so we start with a pre-target theory E, and then the recursion is, of course, I just remind you how it goes. We take and recursion the Euler characteristic. Basic idea is to remove pair of pants, and they are embedded in such a way that they are embedded around the minus boundary on each connected component. When you remove it, the Euler characteristic goes up by 1, and since we're only looking at negative Euler characteristic surfaces, we must end with those of characteristic minus 1 this way, and they are pair of pants and 1 whole tori. And so, of course, in order to run the recursion, we need a target theory. A target theory has this disjoint union bilinear map, and it has this gluing map, which is also a bilinear map. We have some starting data, which is the thing for the pair of pants and the thing for the one whole torus. And then we have this recursion data, which is B and C. And then we stick it into this formula here, where we sum over all pair of pants of this B type, and we glue B to what we have recursively already constructed of the remaining surface, which is always called sigma C. Same thing in the C case here, and we sum this.
Can we explain just this in B case? Don't you understand to have two C's on the left? And you said it's have only one.
Well, I have one thing in the B case on the right.
And so it's a rotation kind of wrong here.
Yeah, so, I mean, there are two C cases, but the remark was that in order to match up with topological recursion, we do not distinguish these two cases, because we could have had a C and a C prime, but we don't. It could one can very easily develop a theory where those two are different. Okay? And then the remark about B is that, well, if you take a pair of pants, so this is the in, and there are two outs,
so
and there's two choices. Either this goes to the other boundary or that goes to the other boundary.
Yeah.
The other one has to be interior. That's why there are two B's. Okay. But there could also be two C's. But Bertrand chose not to have that, and then we follow that to match up well with topological recursion. But if you like to have a theory where it's required that these two are different, no problem. The theory can be constructed. Okay, so we need admissible initial data. So initial data are just these A, B, C, D. I don't really tell you what these specific decay conditions are. I will do it towards the end of this lecture if we're lucky. But at any rate, under certain decay conditions, the theorem is that when you run this recursion, you get well-defined vectors in these vector spaces, and the sums that define it is absolutely convergent. So they're mapping class group invariant. They're functorial. Very good. And skip the proof that I talked a little bit about. Here is the overview that I also mentioned. We skip that. Just remind you very briefly that the Teichmuller space I'm interested in this case of bordered surfaces, is this one here, usual thing, but the equivalence relation is the one where you require that this composite we talked about yesterday is the identity on the marked points. And that means the Dean twists are non-trivial. The Dean twists that are parallel to the boundary. Okay, and so we discussed how to build a full target theory using continuous functions on Teichmuller spaces, and I gave you these explicit descriptions of the Teichmuller space of a pair of pants. So without the marked points on the boundary, it's just r plus to the 3. With the marked points to the boundary, it's r plus r to the 3. And if you divide out the boundary parallel Dean twist, you get r plus u1 to the 3. Okay, that's important to remember when we go on. I then showed you, the gluing maps and the disjoint union maps, and these particular, analytic estimates that I need in order to make this work with the sums. But then we were sort of getting into this, and this is the Mirzakhani-McShane initial data. And the point about this, as we discussed, was that you make these very explicit A, B, C, which only depends on the length and the boundary components of the pair of pants. D is just the sum where you just take a one-hole torus and you just cut it into all possible pair of pants. But you see this pair of pants is strictly speaking not embedded because the two ends of the pair of pants go together. So we didn't somehow, but it is just defined as if it was allowed because you just sum C over this, where this is the length depending on sigma of this gamma. This is gamma. This is the length on the boundary. Here is L sigma of the boundary. So that's the length of this one. And so you see it's a C of that and then two insertions of that. And then you sum over all gamma and you get D. Okay, very good. And so the theorem is that this sums to 1. Okay? And so this uses Mirzakhani's fantastic idea, actually. And so what is her idea? How do you prove something like this? So here's just a few words about the proof, because that will inspire us when we go to the open case. So first of all, you say, let's take the uniform measure on the boundary whose total volume is the length of the boundary. So if I integrate this measure over the boundary, I get the length. But now what I do is I try to compute this integral in a different way. So I take a point here, and what I do is I shoot a geodesic orthogonally away from the boundary. So I'm at some specific point in Teichmuller space, which I'm thinking of as a hyperbolic metric on the surface with geodesic boundary, and now I shoot a geodesic orthogonally from the boundary. And so there are 3 different things that can happen to this. This guy can, in one instance, end on another boundary without intersecting itself on the way. That's case 1. Then what can happen is another geodesic could do the following. It starts here, it goes around, and then it hits itself. And the third possibility is that it continues running forever on the surface. Okay? It never ends. And so it will dance up on something. But not necessarily on the whole surface, but it will dance up on something. And now, so let's call this case B, let's call this case C, and let's call this case empty. And so it turns out that empty is a subset of the boundary that is of measure 0. So I can luckily forget about it. And now let's look at B and C. So you see, if I take now a little tubular neighborhood, so I just erase this guy, we don't need it right now. And so maybe it's stupid that I've done it on the same boundary component. I'm going to erase C also, because else it doesn't work. So what I'm going to do is I'm going to say that, if I take a curve here which is parallel to the boundary, of the surface, but then runs parallel to this curve, runs around this boundary and comes back, what you see is I have embedded pair of pants now of type B. And so the point is that you simply want to measure here in the boundary how long an area you have in such a way that it gives exactly this pair of pants up to isotopy. And so the answer is that's. So that's how B is computed, and Mirzakhani computed that. And likewise, if you do C, you go out and it hits itself, and you do this exactly the same. So maybe I just do a new drawing over here, like this, and you have a geodesic, it comes out and hits itself, and then you take boundary parallel, like this, and you see now it splits into two components. There's also this guy in the interior here. Now it's again an embedding of a pair of pants, but it's now type C. And then you compute how much of the area is it that the geodesic has this behavior here, and you get that expression here. That's what Mirzakhani did. And so you realize that it does not depend on the entirety of the surface, but only the embedded pair of pants. And that's sort of the reason why you can write these formulae just in terms of the length of the pair of pants that you're embedding. Okay, very good. So I will skip the next example, which was the Kurtsevich initial data. We went through that and saw that it was given by psi classes. But what I really want to look at now is these functions. So let's take a function which is continuous and which is decaying at infinity. In fact, it doesn't matter whether it's continuous, not just as long as it decays very fast at infinity. But if you want the output to be a continuous function, this has to be continuous. So now for any surface, you take the set of multi-curves on sigma, and you sum through that set, and for each element in that, each multi-curve, you take a product over the components of the multi-curve, and you apply f to the length at the sigma you are at in time space of the component. So that function is well defined if you have the following condition, that 6g minus 6 plus 2n, where g and n are the genus and the number of boundary components of the surface, is less than sf, where sf is the infimum of this sort of polynomial growth rate measure here. So if that guy is smaller, that means the function decays sufficiently fast that this here will be a nice continuous function. The whole sum is absolutely convergent and defines a nice continuous function that is Markov-Klaus-Group invariant. And that is on a connected surface, and then if I want the things on the disconnected surface, I just multiply over the components, and I start by defining fp to be 1. Okay, and I want to stress that actually I also consider the empty curve as a multi-curve, and that returns the function 1. So this guy always starts with 1 plus more stuff. Okay. So that is sums over multi-curves, and now of course the question is, are these functions, do they satisfy geometric recursion? And so the theorem is that yes they do, and it's actually very easy to figure out what the initial data is. You don't do anything to A, you keep that at 1. B, you take Mirzakhani-McShane initial data and you add f of the boundary that is interior. Remember, this is L, so let me just, so if you have a B here, so a B, for example, is this. So the notation we have is this is L1, this is L2, and then this is little script L. So when you look over there, that's exactly how it is here. And in the case of a C, which I can maybe draw here, so something like this, where I have one like this. So this is a C case, then you have L here, and you have little l here and little l prime here. Okay, so because of the base points and so on, there's a way to distinguish L and little l. But actually what you know, of course, is that because you need diffeomorphism invariant, this guy always has to be symmetric in L and L prime. And you see the expression is symmetric. Okay, and so what you do is you take Mirzakhani C, Mirzakhani-McShane C, and then you couple it to F this way here with the B, and then finally just take the product of the F's on the two lengths. D you define the same way, just actually take its definition. And then the theorem is that if you run a geometric recursion with this initial data, you will get this function. Okay. So now, and yeah, it's a very important point here. So the main idea of why this works is because if you take a multi-curve on such a surface, there is always a pair of hands around the in-boundary which does not intersect the curve, the system of curves. And that's simply completely by definition, right? Because if I look at my surface with the in here and maybe some outs and lots of topology, and if you have a multi-curve, so for example this here, you see the thing is that you're never allowed to take a boundary parallel copy of L because they are not allowed to be isotopic to the boundary. And so therefore, even if I make it as tight as I possibly can, you see there is still a pair of pans here of C-type that's in the complement of the curves. I mean, the boundary intersects the curves. In this case, they are equal to the curves. But that's actually why there is this term here in the contribution. So you can always put a pair of pans in the complement of any gamma. And that's what somehow allows you to show that the recursion is running and giving you this function here.
So they compose in pairs of pens and the curves, all curves and new curves.
Yes, yes. Yeah, so you sort of look at those sum and then you match them up in pairs and so on. Okay, so now let's do the following. So if I have a continuous function on type space, which is gamma invariant, then what I can do is I can consider the Ray-Peterson volume on the type Muller space where I fix the lengths to be L1 up to Ln. And in fact, I can look at the moduli space of such because I can divide out by gamma sigma, right? Because the function is invariant. So I will get a function on this moduli space here of hyperbolic surfaces with lengths L1 up to Ln. And I can integrate it against the Ray-Peterson volume form, provided that such an expectation value exists, provided this integral exists. Okay. And so the theorem is that for those functions we just saw before, these functions here, it turns out that these functions are integrable on this moduli space. So these exist, and the following very nice recursion is satisfied by their averages. So you see what goes in here. So here is the guy for the genus G and n bounded components, L1 up to Ln, was the sum m equals 2 up to n integration over R plus. Then you have this kernel B here, which was completely explicit, right, in terms of f and the Mirzakhani expression. You multiply onto the average of where the number of boundary points have gone down by 1. You insert an L here, you remove that guy, and you do LDL. Plus, and then you have the C term, which works just the way we have now seen several times in Bertrand's talk. And then there is starting data. If you want the average for a pair of pants, length L1 up to L3, well, that's just 1. And then the one for the torus is the volume of that moduli space. So that's pi over 6 plus L squared over 24 plus, and then just the simple average of the function LDL. So therefore, you don't need to know the function itself to compute its average to arbitrary G and N by just running this recursion. So, in fact, and I just want to stress that these two here are given explicitly. I just go back and show them to you. It's just these explicit functions here, right? Where these functions here were, sorry, just go back and show you. There they are.
So this ABC can it's our ABC transit with this continuous index, yeah?
Yes, yeah, something like this.
And satisfies the same.
Yeah. Mm-hmm. So, in other words, I get a completely explicit recursion for the averages here, which don't require me to compute these functions. Of course, it can be very difficult to compute these averages over all curves on moduli space, right? But I don't need to compute the averages. Okay, and so really what this means here is that I run GR, I get functions. If they can be integrated, then they satisfy this recursion here. Actually, I'm only doing it for this specific function, but it actually turns out that any production from GR will satisfy this recursion here on averages if they're integrable. And so this is actually just a manifestation of topological recursion. And I'll just show you exactly how now. So, Well, first I want to show you actually in general how you can start with an instance of topological recursion and lift it to geometric recursion. So, suppose you are given the setup of topological recursion. So that means you're given a spectral curve and you're given a 1 form and a 2 form. Topological recursion produces omega GNs, as we've seen now in Bertrand's lectures. And so the theorem says, okay, you take the spectral curve, it produces the omega GNs. Now you take R to be the set of ramification points of this double cover here, this ramified double cover. For every R, you pick local coordinates near R in such a way that the holomorphic coordinates near R is simply just z goes to z squared over 2 plus some shift. Then you let V be the free vector space on the ramification points. Then the theorem says there exists a family of admissible initial data parameterized by some real number beta in R plus, such that you can use the target theory, which is continuous functions from Teichmüller space, to V, which is this vector space we just constructed here, tensor power the number of boundary components. And the GR amplitudes, okay, for some initial data that is specified by the curve here, are integrable over moduli space. And when you perform the integrals, they give you exactly the same as these residues on the topological recursion side. And notice this is a Laplace transform on the outputs of the integrations.
What is the role of beta?
The role of beta is to take a limit here. That beta has to go to infinity. Yeah. So the thing is that the way you should transform between what we have here and what you have in topological recursion is simply just the Laplace transform in the lengths and the boundaries. So in other words, if you do the Laplace transform in the length of the boundary, I mean the LIs here, you will see exactly topological recursion here. This is topological recursion in disguise. It's just you've applied the Laplace transform or it's in. So therefore, any instance of topological recursion can be lifted to geometric recursion matrix. And it gives the same output. Okay, so now suppose we start the opposite way. Suppose we have A, B, C, D, which is initial data for geometric recursion, which satisfies a certain stronger admissibility condition. So I don't want to go into the analysis of what that is right now. But under some good conditions, then the GR amplitudes that you compute, the omegas, they satisfy that they are integrable over the moduli space. And so you can talk about the WGN of L, simply just these averages, where L now is a multi-index. And then if you define W03 to be A and W11L to be this average here, then the output satisfies this. And so that is just, this is, as I just showed you before, this is just a manifestation of topological recursion. So, in other words, if you start with showing that something is given by geometric recursion for the target theory Teichmüller space, and you average over moduli space, your result will satisfy topological recursion. So it's a way to prove that something satisfies topological recursion.
I mean, topological recursion in what sense?
Yeah, in the sense of this. So in the sense of
points,
in the sense of this, which is, you know, under this Laplace transform, exactly the same as what we saw before. So under this transform here, the two are taken to each other.
But before you have kind of not only function, but function with some labels on the boundary.
Yeah, that is right.
Yeah.
And this is to encompass the general topological recursion.
Yeah.
Here I say now I start with a general geometric recursion for Teichmüller target theory.
Yeah.
And then I don't need these labels on the boundary, I just get these functions as averages. And they satisfy this, and I'm just saying this is a manifestation of topological recursion, because, you know, it's the case where this vector space is one dimensional is V. So, you know, whether you have a recursion like this or you have, well, sometimes it's more efficient to actually have topological recursion and have the spectral curve and run it this way, right? But essentially the recursion is just the same as the one that's here. Okay, very good. Now I want to, so that was discussion about what is the relation between geometric recursion and topological recursion. But notice I only discussed that for the special target theory continuous functions on tight limit space. So geometric recursion applies to many more targets, right? Not just functions on tight limit space. For example, it applies actually to functions on higher tactile components. So if you look at Hitchin's higher tactile components, you can use, instead of length of geodesics, you can use the spectral radius that is used in the pressure metric, and you will get things that satisfy geometric recursion also, and you can build functions on those. So, expressions as I had before, like these sums over lengths like this makes sense for higher tactile theory also. It gives nice continuous functions there. Okay. All right, but now I want to show you a new target theory. Okay, so I'm still with tight model theory, but now I will not look at functions on tight model space. Now I will look at forms on tight model space. And so what I want to do is I want to look at this special tight model space that I have for pair pants. So remember, the one for pair pants is r plus cross u1 to the third. And I have these coordinates, the 3 lengths of the boundaries and the 3 twist parameters of the boundaries. And if I look at a one-hole torus, then I have the coordinates r plus cross u1 cross r plus cross r with differential-Nielsen coordinates. You know, this is the length of the boundary, this is the twist of the boundary, and then L and phi are the lengths of, say, this curve here and the twist around that curve. So that's L and phi. Okay, so now I define, so the target theory is now defined to be the total space of forms on these tight mode spaces. And I now define A to simply be X with respect to wedge product of this symplectic form on the 6-dimensional space associated to a pair of pants. And you see, this is really symplectic because I've added to every length, I've added a dual coordinate, the twist parameter. And that was the sort of point about having these base points on the boundary that allows me to have a symplectic space associated to each of the surfaces, even though they have boundary. So that's what A is. And B is very similar, except you take the B from the Mir-Sakane-McShane function for B. You multiply that onto where you do the same thing, but only take the 2 in boundaries, so to speak. And you only take, where's the B? Here's the B. You only take this exponential, so you only take the full form for these 2 boundaries that are also common to the surface, and then you take this form here in the interior. And finally, for C, it only has 1 exterior boundary, right? So you multiply it with the Mir-Sakane-McShane for C, X of that form, and then you wedge with these 2 here for the 2 interior boundaries for C. And for a torus, you just take X of the Weil-Petersson symplectic form on the cycloidal space of the torus. Now the theorem is, if you run the recursion for these, you will always get X of the Weil-Petersson symplectic form. So X of the Weil-Petersson symplectic form can be obtained this way. In particular, the Weil-Petersson form itself can be obtained because that is the one, that's the one in degree 1, right? So this series starts with 1 plus the Weil-Petersson form plus the Weil-Petersson form squared and so on. And also you also obtain the Liouville measure, right? Because that's the top power of the Weil-Petersson symplectic form. Okay, very good. So I think now I will skip, for the moment I will skip this. I'll come back to it, but I want to show you, and I also skip this, I want to come to this example here. So that was the 3rd example I gave. The target theory is now back to functions on tight mono space, but the function I take is the trace of f applied to the Laplace-Beltrami operator. But you know, with either directly or Neumann boundary conditions, because we're looking at surfaces with boundary, right? And so I don't know if this function here satisfies geometric recursion. I expect it doesn't, but I don't know. But what I do know is that, of course, Selberg proved his famous Selberg trace formula, right? And that expresses this function here as, well, some specific function here and some things to do with the boundary here, but then these 2 here are sums over certain subsets of primitive geodesics inside sigma. Yeah, primitive means that the geodesic runs once,
But not simple geodesics.
but not simple. Exactly. Because simple was the ones we had before, but now they self-intersect. And so if I take a geodesic on a surface that self-intersects, this geodesic might fill the surface up completely, so that if I cut along the geodesics, there's only triangles left. So therefore, I cannot fit a pair of pants in the complement of a geodesic. And that's the reason why I can't use the same proof as I had before to prove that this function here should satisfy geometric recursion. But of course, this gives you an obvious thing to say, or to do. It's simply to say, well, let's not remove pair of pants. Let's remove what we definitely must see. And so if you have three geodesics on a surface that intersects like this is possible, right? You can never have one geodesic that encloses, something contractible, because then it's not length minimizing. And you can never have two geodesics that intersect like this, right? Because then they're not length minimizing either. But you can have this. So therefore, obvious, right? Two things that needs to be changed. You change from surfaces with boundaries to surfaces with corners, and you don't extract pair of pants, but you extract triangles. So that's exactly what we do in open geometric recursion. So now I consider a new category. This is the category of surfaces with corners. So I will consider compact oriented surfaces with corners with a mark point on each boundary component, and this mark point must be a corner if the component has a corner. Okay? And then we set the total number of corners and mark points to be C of sigma. And of course, all the corners must be in the boundary. It's a manifold with corners. And then I define this funny quantity here, chi C, which is 3 times chi minus C. And I'm going to recursion that. Okay, and so what we also want the category to have is that we want a specific in mark point on every component of the surface. Okay, so let's just make a few drawings to see what we're doing. So first of all, let's look at this one here. And so this guy here, let's look at this guy across the surface. So this guy here has Euler characteristic equals to 1, and it has C of sigma equals to 2. So 3 chi C of sigma is 3 minus 2, which is 1. That's not allowed, because I require that this is less than or equal to 0. So the first guy of Euler characteristic 1 that's allowed is a triangle. So it should have 3 corners, right? Like this. Then there should be one that is a mark point. Let's say it's this one here. That's the corner that is marked. And then each component should have a specific marked point. And so that's this one. That is the in, and the rest is out. So I record them with pluses. Of course, correspondingly, I can continue with the Euler characteristic 1. Let's say this is marked in, and the rest is out. And so on. And you'll notice that you can also have a cylinder actually. So you cannot have, so what you can have is this. So you cannot have the cylinder without any mark points, but it's a requirement that each boundary has at least one mark point. So you can have one like this, and so this is maybe the in, and this is the out, so that's allowed. And this can either be a mark point, so a smooth point that's marked, or it can be a corner. Okay, and so on. Put some more topology in them or something like this. Okay, so those are the surfaces. And of course, the morphisms are just isotopies. So isotopy classes of orientation preserving diffeomorphisms preserve both the set of all marked points and the subset of the in marked points, modulo isotopies that also preserves all this structure. And these are diffeomorphisms, so of course they preserve the corners also. Okay? Very good. So let's take such a surface with corners. Then of course what happens is that the corners are splitting the boundary components into segments. So like over here I have 3 segments, right? This one, and that one. this one, this one, this one. In this case, you have one segment. And of course, what you can see is that the segment might have the topology of a circle, and that happens if and only if a given boundary component only has one mark point. Very good. And now a pre-target theory with corners is a function from this category of surfaces to vector spaces again. Okay, good. So now, here's sort of the analog of the slide that I showed you before, but now for this open geometric recursion. So we start with this pre-target theory E. We are seeking to define vectors that are mapping class group invariant for all upper mapping for all surfaces. We're going to recurse in this chi-C, and the basic idea is to recursively move triangles and cylinders.
Lost, because when we consider this not simple geodesics, yeah?
Yeah.
Then the complement would be not only triangles, it would be polygons as well.
Yeah, that's right. But that's fine. But the worst it can be is triangle in terms of.
Why do you have only triangles?
Yeah, well, remember that when I did the other curves,
Yeah.
I only had pair pans.
Yeah.
And that's because it's much more efficient to only have these small pieces. You could imagine a theory that takes sums of all kinds of topologies, taken out of all kinds of topologies, but it sort of, it means that your recursion data has to go up, and then, you know, it's not, this is much nicer, and it works. So, it's important you have both triangles and then these cylinders. Okay, I'll show you why in a second. Okay, let's say I have triangles and I have cylinders, and for the triangles, so what I require is that the triangles are embedded in such that their minus vertex, it goes to a minus vertex of the surface. And you know what happens is that, I'll show you in a slide after this one, that this chi-C is exactly concocted in such a way that when you extract these triangles or these cylinders, this chi-C goes up, and it ends with chi-C equals to 0, and the only possibility for chi-C equals to 0 is a triangle. So what you will be doing is recursively remove triangles and cylinders until the rest is triangles. Okay, and so of course, can you see this picture here? So what it is, there is an outer boundary here and another boundary here. There is the minus point for that component right here, so the triangle has to start with a vertex at the minus. It's embedded into the surface and goes across the surface, so both these two edges are interior to the surface, and it hits an arc in another component. So the requirement for the embedding is that the vertex goes to the in vertex, and the rest of the edges either have to be edges of the boundary, either has to be arcs on the boundary, or they have to be interior arcs. So in this case, there are two interior arcs and one at the boundary. In this case, you have a triangle inside a square, so it has two boundary arcs and one interior arc. So those are the allowed triangles. And for a cylinder, what I allow is that the curve, the outer curve starts at a vertex, the minus vertex, goes around on the surface, comes back, and the other boundary on the cylinder is a homotopy class of a simple closed curve on the surface. So those are the three things that are allowed. Of course, there are many more combinatorial types of these guys than I've shown here. I'll show them on the next pages. Okay, so I do exactly the same as before. A target theory is something that has also disjoint things, and it has ability to glue. And then the starting data, what is that now? Well, of course I have to have something for a triangle, because everything stops with a triangle. So I have starting data, which is A for the triangle. And then you see I have recursion data, and recursion data is this type here, where I call this an interior triangle, and this one here I call a boundary triangle. So there are two different guys that lies in E of T, which is a triangle, and then I have a C, which is in E of a cylinder, but the cylinder has a non-trivial mapping class group because I can rotate around, beam twist around in the middle, right? So I have to have that C is invariant under that action. And now I simply do the same as before. I just sum over all triangles that are interior, all triangles that are boundary triangles, and I use the sewing morphism, stick in BI here, BB there, and C there. And of course, recursively, sigma C is the rest of the surface, and recursively have already defined these guys here, right? Because they have higher chi-C than I have with this instance. Okay, good. So let me just show you a few examples of how these guys can be. So, for example, here is a triangle, like the one I showed before. Actually, it's a triangle that goes from one boundary to another. Here is the minus in vertex, and then it goes over to some arc here, fills out a triangle like this. And so what happens is when you cut it out like this, you have this remaining. In this case, here's the Euler characteristic goes up by 1, and the number of boundary corners goes up by 1. So therefore, this is chi c goes up by 2. Because of 3 times the Euler characteristic minus c. That's why it goes up by 2. Here you have where you do a triangle that connects a vertex to the same boundary component, to an arc somewhere on the boundary, to a segment, as I defined it before. When you cut this out, you get a similar behavior on the Euler characteristics. And here you have, where this triangle is embedded in such a way that the end point of the arc that goes around here is the same as the vertex you start with, so that's also allowed. And then you get this, and so you constantly keep track of how the chi-c is behaving, and you see that it's going up under all possibilities. And so here there are actually 6 different cases for the interior triangles, and you could make the recursion kernels different for all these 6 if you want to. And then there are 4 boundary triangles, and 2 of them are sort of obvious like this. And then there's these 2 less, or sort of where you have a triangle sitting along a boundary like this. You can remove those also. Now the chi stays constant, but c goes down by 1, and so you also have that this thing goes up by 1. And finally, here's a cylinder removal that also has the chi c going up by 1. Okay, good. So now we simply say, let's specify the initial data that we need. So that is A, B, B, and C, BI and BB. And then there are certain decay properties again, that I'm not telling you about right now, but under certain nice decay properties, we get exactly the same theorem as before. You use this recursion over and over again, and then the point is that under these decay assumptions, you get absolutely convergent series, so this becomes a mapping class group invariant assignment like this. Very good. So now, let's try to do this for Teichmuller space. So the Teichmuller space I want now is a little simpler, because the Teichmuller space is simply the space of hyperbolic metrics on sigma, such that the inner angles at the corners are less than or equal to pi, and all segments are geodesics. So now I just think about hyperbolic geometry. So, for example, if I look at a triangle, what do I have? Well, I have, for example, the 3 inner angles here like this, and they can be anything from 0 to pi, but of course, by Gauss-Bonnet, if you want a hyperbolic metric on it, the sum better be less than pi, right? But that's the only constraint. And so Teichmuller space is just that for this triangle. The lengths are determined by the angles. And so for a cylinder, what you have is that if you look at the length of this interior closed smooth geodesic, and then you look at the length of the distance from the apex here on the other boundary component and into this one here, those are 2 coordinates, and they give you faithful coordinates, global faithful coordinates on Teichmuller space of the cylinder, and just gives you this. Of course, notice that if you want to make this angle here also pi, so you want to smooth it up, then what happens is that the area of this guy disappears, and you end up with just a curve. So that's not allowed, of course. So that's why the length of L0, obviously. Sorry. Yeah. Just wanted to show you that. I mean, normally we say that there's no hyperbolic metric on a cylinder, but that's because we assume that the geodesics are the boundaries of geodesics and smooth geodesics. But if you allow corners, there are plenty of examples. Okay, good. Those are the 2 Teichmuller spaces. So therefore, initial data will be things that live on those spaces. And so now you consider the following Mirzakani-Marchais open initial data. So A is still the function 1. And now BI and BB is the same function. It is namely depending on some A0, which we get to in a second. But else all it does is just take the alpha angle and divide it by a alpha 0. So remember the alpha angle was the one at the end here. And it just takes and divide that by some alpha 0 we're going to specify in a second.
This is much simpler than this.
Yeah, it is. But that's because you see, it would be something like this if I wrote it in terms of length. Yeah. But it shows the angles to make it simple. And then actually there is some function here, which I didn't give you. There is an explicit function that involves lots of signs and hyperbolic signs and so on for this as well. because I chose lengths here. But it's not, it's nice. Okay. So the theorem says the following, and I just formulated it for connected surfaces. So if you take a connected surface to the corner, and you run the open geometric recursion applied to this initial data, where at the corner, so at the specific in corner you have, for alpha 0, you take the total angle at that in corner. So let's try to draw an example over here. So maybe you have something like this. Maybe this is the in corner. So it has some angle. So C sigma in this case is just 1 point. C sigma minus just 1 point. And so this here is simply alpha of C minus sigma, which is the total angle at that point. And then, so what you do is you take B and C and so this B here means either BI or BB since they're equal for that angle at this corner here. And then you run the geometric recursion, the open geometric recursion. And the theorem is this gives you 1. So this is a Mirzakhani-McShane identity for the surfaces with corners. So yeah, I think it's completely new. And the proof is actually again the same. What you simply do is you just say, well, if I take a uniform measure on angles here and I integrate it up, I will of course get alpha. But now let's try to do the same game again. For any point here, so for any angle, I shoot a geodesic into the surface. And so again, 3 things can happen. It can go to the boundary. If it goes to the boundary, well then I draw a triangle embedded around this. If it doesn't go to the boundary, it will go around and hit itself. That will correspond to cylinders. And if it goes and runs forever, it's measure 0. So therefore the integral of this is the sum of all pair of paths, sum of all triangles and cylinders embedded in the surface and some contribution, and they are the contributions again. So the scheme is the same. And so that's why this identity works like this. And so now that's great, because remember before it was really essential we had this partition of unity. Because with this partition of unity we can do many more things now. So let's let's face it. Let's look at immersed curves. So the I sigma will be the set of isotopy classes of immersed curves in the surface, such that the boundaries of the curves goes to corners. So now it's arcs, it need not be closed curves, right? It could be arcs, but they have to go from corner to corner. And no 2 components are isotopic. Further, no component is allowed to be isotopic, rel boundary points, to a segment of the boundary. But it doesn't, you can have a situation like the following. You can have a boundary that looks like this maybe, so it has one corner here. Then you can have a completely smooth guy like this, which is isotopic to the boundary. That's allowed now. And notice that cuts out the cylinder we're looking at over there. But you cannot have this, that you have some guy that runs like this and then comes back here, because that's isotopic to that arc in the boundary. Okay, good. So now we take again a function that decays very fast at infinity, and we form this entire big sum here. So now we are summing over all our immersed curves instead. And for sufficiently fast decaying f, now there's a little bit more constraint on f, but still, one gets that this is an absolute convergent sum, gets a nice continuous function on type molar space, and it's mapping class group invariant because these are just permuted again by the mapping class group. For disconnected surfaces, we multiply them together, and for a triangle, we just take the function 1. Okay, good. So now, here is the complete analog of what I did in the closed case with the F twisting. So this is F twisted Mirzakhani-McShane open initial data. No change on A. B with an F on it, with the B here up here, is just the Mirzakhani-McShane open B plus F of the length. And the interior guy is a little bit more complicated, so it's the I from our identity from before, Mirzakhani-McShane in open case, and then the B for that multiplied by the 2 F's of the 2 boundaries. Remember, this B here is where there are two edges of a triangle that's interior to the surface. And then there's again the product we saw from before, and then the cylinder guy behaves like this. And then the theorem is if you run the open geometric recursion on this initial data, you get this guy. And the argument is exactly the same again. This thing that when you want to somehow understand, improve by iteration, that this function is given by the recursion with these recursion kernels, you will exactly be faced with the same thing. Now you have sums over triangles and cylinders, and you have sums over all immersed curves. But the nice thing is that every time you have an immersed curve, there's always either a triangle or a cylinder in the complement of it. And so you can again interchange the two sums and prove that the recursion works. Okay. Yeah, and so that's what I just said at the bottom here. Very good. So coming back to this guy here, looking at this spectral guy here now, well, you know, by the Selberg transform, I only stated it for surfaces without corners. There is an analog for surfaces with corners. It's more complicated than this. But so you see, if you want to understand this guy, all you've got to do is understand these sums over geodesics, primitive geodesics. And so the theorem is that when you look at this guy like this here, and f is sufficiently fast decaying, you take the either directly or Neumann boundaries, then this function here will satisfy open geometric recursion, the spectral guy here. And when you average over the subvarieties of the quotient by the mapping class group where you fix the boundary length and angles, then this will satisfy some explicit topological recursion like recursion. But now, where you don't have pair pairs, but you of course have triangles and surfaces topologically. Okay. So this is completely explicit recursion. I didn't write it out here. It's sort of lengthy to write it out because it had all these special cases that I showed you. But there is some nice recursion that allows you to compute the averages of these guys.
It will begin a structure.
Something like this, but
It's something else.
yeah, that's right. Now it's triangles and cylinders. So I think this solves, you know, big problem in analysis because understanding averages of these functions here over moduli spaces, you know, this has been a big issue. I talked to Sanak and several other people, Seldic and so on. They say, yeah, this is amazing somehow. I mean, you know, you actually can do these ones here. So you can compute the averages of these now recursively via the scheme. Okay. So yeah, a little bit of time left. So I could decide to torture you really wildly the last 9 minutes with the actual definition of the target theory. And you know, maybe I just allow you to read a little bit so you can see what you're going to be faced with. So you're actually not going to be faced with just one vector space, but you're going to be faced with a directed set and an inverse limit of Hausdorff locally free, Hausdorff complete locally convex vector spaces in such a way that you're going to take a limit. And then you're going to have this thing, of course, has a limit because there are limits in this category that I'm working with of vector spaces. These Hausdorff complete locally convex vector spaces have limits. And then there's an important subspace where all the semi-norms are bounded. And you're using, so that norm is not always finite. And then you have some kind of systems of inclusion, blah, blah, blah.
That's kind of nuclear pressure space.
It's not the same as that. But anyway, I mean, there are the point is the following: that if you, for example, look at the target theory Teichmann space, it turns out we cannot prove that our sums are universally uniform convergent over all of Teichmann space. But if we take the subset where the system is bounded below by some epsilon, then we can do it.
It's on compacts.
Well, not on compacts, because it has to be mapping class to be written, but on system sets. Yeah. So first you have norms defined on compacts inside system sets. And then you take a limit over system sets. And so this I here, you can think in that example as the real line, and epsilon running in there, and then you're taking these system sets and getting it to work.
But it's compact in quotient.
It's just compact in quotient, but not in the Teichmann space, and we're working in the Teichmann space, because before we've done it, we don't know if mapping class will be right. Okay, and then, you know, it turns out that a real target theory is something where you have these, you know, directed sets of these vector spaces. I don't want to keep repeating all the conditions that these vector space satisfies, what I've said all the time. But then it turns out that the thing that indexes seminorms on this vector space should also index length functions. And so seminorms in that vector space is indexed by compact subsets inside system sets. And so, for example, in the type space case. And so length functions are supremum over the compact subset of the length function from hyperbolic geometry. And that's why the indexing sets correspond in that case. And so then you work with such a thing like this, and then there are three axioms that has to be satisfied. The polynomial growth axiom says that, you know, for all I in this directed set and all the seminorms for that I and any else positive, you have to have that if you look at the things that have length in this notion of length less than L, then that set here should be finite, and there should exist two constants such that the supremum over all the what indexes the seminorms, so this is these sets here, that thing here should be only growing polynomially fast. And then there is some more things, so there is something called a low bound axiom that has to do with that there is not too many small pair of hands. Lower bound axiom, means that, you know, the length functions have a universal lower bound when you look at some I and look over all seminorms and all curves. There has to be a uniform boundedness, and that's the system. That's the analog of the system in general. And then there is the small pair of hands. There cannot be too many small pair of hands. And then you have to have these gluing and union axioms. And if you have all of this, and you have, I go fast because I think it's impossible to absorb in these 10 minutes, but then these are the exact analytic conditions that you have to have in relation to all the seminorms involved and blah, 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 blah. So they're right here, and when you have those, you can indeed run precisely what I was telling you in the beginning about these sums are bounded by these zeta functions that are defined now in terms of these here, and then you get that the things are absolutely convergent. And so I just show you what I've said in words along when I was showing the previous slides now, is namely that the way you do this for type space is you look at system sets, and then you look at compact subsets inside system sets, and you use those to give you all of these seminorms that give you the topology of the vector spaces and this inductive set of the directed set. And you use various things by Rabin and Mirzakhani and Hugo Pallis, results on a small number of pairs to show the type space indeed satisfies all of this. And then the whole thing runs. So I think I just stopped there. So thank you very much for your attention. Yeah.
So is this open geometric recursion in any way related to open intersection theory, so moduli space of ordered Riemann surfaces?
So open geometric recursion has not existed for very long. so maybe, I don't have anything to say about that. Maybe it is.
So the naming is not too common.
So the reason for open is because it mirrors open string theory. Because before you had closed strings, because it was all boundaries were circles. Now the boundaries are arcs, and so that's why it's called open. So just because of the string theory. Yeah.
Is there any other application that you can show us something interesting with other than the target spaces which are not related to the type Miller space?
Yes, there is actually a lot of work now being done on combinatorial type Miller spaces. And so are you here next week? No. There will be 4 talks on this next week, and 2 of them are about combinatorial type Miller spaces and actually, doing various things with those, in particular constructing combinatorial French and Nielsen coordinates on those, and computing combinatorial volumes on those, and we get a new proof of Maxime's result of the Witten conjectures this way. But it has to do with type Miller space, but now a combinatorial type Miller space. And what I can tell you is that if you look at these higher type Miller spaces, so that's not hyperbolic geometry anymore, then if you choose these functions f with sufficiently fast decay, what we can say is that then the function is actually integrable over the higher type Miller component divided by the Martin class group. But the mapping class group is a different mapping class group now. It's a sort of special one. But nevertheless, so normally if you take the higher type component and you divide by the mapping class group, this does not have finite volume. But if you multiply on these functions on the measure, then and divide by a bigger mapping class group we can afford in this case here, then actually this thing has finite area and finite volume, and we get formulas for these in terms of this machine.
What is the bigger technical group?
Yeah, so the bigger mapping class group is given in terms of Dehn twists. Sorry, the mapping class group is given, as we know, in terms of Dehn twists. But the thing is that when you look at these higher type-model components, you need to do more than just Dehn twists. I mean, there is some construction where you twist in some curves that are not simple closed. And so it would take me some time to explain precisely what it is, but it's a much bigger move. I mean, really much bigger. It's closely related to some of the work we've done with Roger. But I mean, I can say, so that although you didn't you disqualified technical space, but one thing is that if you look at closed string field theory, there is actually a way to construct what's called the vertex, the string vertex in that case, by using a very simple function like this. So a function that is the indicator function in the interval from 0 to epsilon multiplied by t, and then 0 the rest. If you run the recursion, you get a measurable function, and it turns out it has this very nice explicit expression where this is the number of geodesics smaller than epsilon. And so you actually can show, I mean, and then the recursion shows that, the boundary, so if you define this set here, like the indicator set of this function, then this satisfies what's called this quantum master equation from closed string field theory. So, but it's type space again, okay? And also, if you look at measure beach volumes, then it turns out that measure beach volumes satisfies a very nice recursion, also this geometric recursion. And now you have to use this function here, applied to length. So, but I mean, I think it's just a matter of time. I mean, I would really, so many people here are interested in things like Fukaya categories, Fleur, homology, cohomology, and so on. And I showed you this target number 15, which involves this targets of, and I really encourage people to try to look at this machinery and see if they can't use it to show that things there satisfies this recursion.
Yeah, but I feel also.
Yeah.
Situation. Can one use instead of hyperbolic metric, like flat metric and some few negative singularities?
I think so.
Yeah, it will be some analogs of Mirzakani identity.
Yes,
So
yes. Yeah.
it will be really goes directly to flat metrics and so on.
Yes, yes. And this is closely related to what I was alluding to before with combinatorial type-model theory. Because there's also a McShane identity there, and there it's finite sums because somehow it's now becomes just as you indicated. So yes, and that was non-type-model, although it was very strongly flavored in this direction. But kind of any kind of length measure that satisfies these axioms. So it's asking for these length measures here correlated to the sets that index the seminorms. And they have to satisfy 3 axioms. So polynomial growth is very important. So when you bound the lengths above by some large L, you will have to see only polynomial growth. Then you have to know that there's sort of a uniform lower bound. And then you have to know that there are not too many small pair pairs. If you have those 3, the theory will run. So you should just think as crazy as you possibly can about such length functions. Because every time you have such things, you can run this. And this target theory can be very different, right? I mean, that can be anything you want.
But it doesn't seem like this has much to do with holomorphic maps. It's more like more rigid maps.
It has a lot to do with hyperbolic geometry.
It's like you should try to know.
So let's ask it in different words. How do we marry, how do we insert hyperbolic geometry in homological mirror symmetry? And I want to just, as a joke, just mention one thing, namely that if you take, let's see, Yeah. Namely, if you take Mirzakhani's initial data, that's extremely important for Mirzakhani-Maxent relations, and you do this kind of scaling to it, you get the Kontsevich initial data, which has a lot to do with the way we normally do it in algebraic geometry, over MG and bar, right? So,
In theory, you some kind of flat metric on the surfaces.
yeah. So I mean, the big question would be, how do you marry hyperbolic geometry and hyperbolic surfaces with, you know, this kind of concept of a symplectic manifold with Lagrange? Is there some good equations that replaces the pseudo-homomorphicity of curves? That I mean, if you have that, I think it would be sort of immediate to implement it in here. But it may not be necessary to have that, actually. But I'm thinking that what we should be looking at is these hyperbolic surfaces with boundaries in such a way that the boundaries are sort of in small tubular neighborhood of this Lagrangian subarites. It's living in the cotangent bundle neighborhood of it. We should do something with that instead. I'm not sure. Actually, if you're looking at sort of Floer homology, then you are looking at surfaces with boundary, and you want them to lie in a Lagrangian, right? Just like I was indicating at the very beginning.
But it's like the corners are different somehow. In Floer theory, you always have like infinite thing, like you require some kind of finite energy condition, but there are actually infinite things mapping in.
Yes.
But this is some kind of compactified. The point actually maps to the intersection of Lagrange's main.
Yeah, but then you might sort of say that I want to look at things where, you know, I've stretched these boundaries off to infinity, but it kind of loses some of the whole game here, because the game is to cut along surfaces with respect to curves, simple closed curve on the surface, and then you know you have some limits where you push those lengths to zero, and you get the usual things in algebraic geometry, nodal curves. So it really has to lift it out and somehow, but I mean, for example, here you do have surfaces with boundaries that lie in the Lagrangian, right? But they, of course, they don't glue so well, these guys. You know. So, yeah. I don't know. It's very good for spectral theory. It's good for talking about statistics now of eigenvalues of Laplacians, and it's very good for statistics of lengths of simple closed curves. I mean geodesics, simple closed, and also now general geodesics. Yeah. Any more questions?
Okay, well, thanks again.